Hi everybody and welcome back. In this lecture we will talk about the necessity of image pre-processing when working in the joint field of medical imaging and machine learning. Before we dive into the pre-processing techniques used, let us briefly recover why pre-processing our datasets when applying machine learning is important. When we pre-process our data, we make sure that it is prepared for training and testing. Thus, there are various pre-processing techniques we might want to test. This includes, but is not limited to, modality-specific pre-processing steps, normalization and standardization, and homogenization of image resolution, size, orientation, and many more. Some machine learning methods may require specific input formats. As an example, you will neither be able to train a network on X-ray images of size 16 x 16 because basically after 4 max pooling operations your feature size will be 1, nor will you be able to train your network on 4K images because current hardware is just not strong enough for this. And last but not least, by converting your training data into more efficient data structures, you will be able to increase the training speed due to decreased access times to your files. In this lecture, we will inspect 5 different pre-processing steps used in the field of medical imaging. At first, we will take a look at some modality-specific pre-processing steps. Then we will briefly talk about orientation and spatial resampling and resizing. The topic of intensity normalization and standardization will be discussed in more detail because it's one of the most important techniques when applying machine learning algorithms. Finally, you will get an overview over different efficient data formats used in medical imaging and machine learning. As promised in the last programming lecture, at the end of this lecture we will talk about the affine matrix. Alright, let's get started. Modality-specific pre-processing deals with the task of finding suitable processing techniques for all modalities. Even image reconstruction algorithms, which are supposed to convert the raw output of the scanner into a form that we humans can actually understand, is a part of those techniques. However, usually those algorithms are directly implemented in the scanner and you don't have to deal with them. Another important task is noise removal from either the raw or the already reconstructed scanner outputs. There are some rare occasions where you want to apply denoising algorithms yourselves, but most of the time the data we deal with as developers is already denoised. Depending on the modality you work with, complex artifacts might occur. Especially motion is a much harder problem when working with CT or MRI data, but not that bad when working with ultrasound. The task of motion correction has its own research field, which is far too broad to be captured in detail in this course. Sometimes motion correction might already be implemented in the scanner, but not all the time. If you have to work with data corrupted by motion, you should absolutely take a look at the current results and algorithms used in this field of research. The last point I want to mention is the importance of quantifying the outputs, or in other words, to make sure that all outputs have the same unit. Most of the time, this technique is directly implemented in the scanner. However, depending on the task and modality, as an example when working with PET images, it might be possible that you have to manually quantify your dataset. After talking about modality-specific pre-processing techniques, let us talk about orientation. The goal of orientation-based pre-processing algorithms is to achieve a standardized image orientation for the whole dataset. As an example, if you miss to handle this step, you might obtain a data set where the first axis sometimes moves from top to bottom and sometimes moves from left to right. Such a data set will absolutely decrease your training performance and might drastically worsen your results. When performing resampling, our overall goal is to get a standardized physical resolution and size. This means that all your scans in the dataset have the same shape and all voxels in all scans have the same physical resolution. As an example, each voxel might cover an area of 1 × 1 × 1 millimeter. This can be performed by either resampling, or if the single voxels already have the same physical resolution, by padding and cropping. Most of the time we use this methodology to reduce the size of our images or volumes. Now it is time to talk about normalization and standardization, which is, as I already mentioned at the beginning of this lecture, one of the most important pre-processing steps for you as machine learning developers. The goal of this process is to get your pixel values into specific intervals. As an example, between -1 and 1 or 0 and 1. This procedure can simplify the learning process for the model and may increase the training speed, the performance of the model, or even both. Depending on the task at hand, you need to use different normalization or standardization techniques. As an example, when dealing with MRI data, you set normalize and standardize per subject. However, in contrast, when working with CT scans, you typically do not need to normalize, but standardize the complete dataset. For highly specific tasks, there are also some advanced methods. As an example, when working with PET images, you might want to compute the logarithm of the single voxel values. Most of the time, when working with brain images, you match your individual brain scan onto the M&E template. You can imagine the M&E template as a card or an atlas of the brain. This template matching approach only works because the brain is extremely similar within all individuals and highly symmetric. The following table contains an overview over the most common modalities and their pre-processing techniques. When working with X-ray images, you at first standardize your data by scaling those images with a constant of 1 divided by 255. After that, you compute the mean and standard deviation of the whole data set to perform set normalization. When dealing with CT images, you typically don't need to perform normalization. However, it might increase performance when you scale the data with the constant 1 divided by 3071. Additionally, depending on the task at hand, you can use windowing or cropping. As an example, if you simply want to focus on the lung, then you might crop away everything below the stomach. Windowing is more or less simply another word for contrast enhancement or contrast changes. In this figure you can see two different windows, one called lung window and one called soft tissue window. In the lung window you can see that this windowing allows a beautiful visualization of the blood vessels within the lung, but it is impossible to see anything within the abdomen. However, in contrast, when using the soft tissue window, we obtain a very nice representation of the abdominal organs, but lose most of the information in the lungs. Therefore, depending on the task, we need to make sure that we are using the correct contrast or window. Since MRI scans are not based on a comparable and absolute unit like CTs are, both normalization and standardization are performed on the individual subject and not on the complete dataset. Additionally, you can again use cropping to focus on the part you want to inspect. As already with CT images, PET scans are typically not normalized, but their values are often clipped in the range between 20 and 40. As already mentioned on the last slide, sometimes it might be also helpful to compute the logarithm of those values. Data received from medical ultrasound can be processed in the same way as X-ray images. Note, and this is really important, all the techniques or suggestions shown here work most of the time and help to improve the performance. However, in some occasions it might be the case that they hurt performance. Therefore, I recommend to always try different normalization and standardization techniques to compare which one performed best. Since machine learning is a really empirical field, this is simply the fate of us engineers. After applying all necessary pre-processing steps, it is time to take a look whether you should convert your data to more convenient formats. When working on raw DICOM files, you should always think about converting them to Nifty or another data format which can handle multidimensional data such as NRRD. Then you might think about efficient data storage for machine learning pipelines. As an example, you could convert your data into NumPy files or use efficient memory containers such as HDF5 or SAR. Now, as promised, we will talk about the relationship between physical and voxel coordinates. A voxel coordinate defined by the three integers I, j and k refers to the position of a voxel in our data array. As an example, when using the values 0, 0, 100, those coordinates exactly identify a voxel in our scan. All voxel coordinates correspond to the physical ones in a one-to-one manner. This means that you can transform each coordinate of your data array to a coordinate in the scanner where the scan was produced. In contrast to our voxel coordinates, the physical coordinates have SI units, millimeters most of the time, and a standardized reference with respect to the scanner. This one-to-one mapping between our voxel coordinates and our physical coordinates allows a transformation between the two of them. This transformation can be computed by multiplying a matrix A with our voxel coordinates and then adding an offset called x origin. This 3x3 matrix A, which is used to transform the voxel coordinates into the physical ones, is called the affine matrix. It defines the linear transformation corresponding of scaling, where you simply stretch or squeeze an image, rotations, where you rotate an image, and shearing or tilting, where you skew an image. Of course, it also contains all possible permutations and combinations of those three linear transformations. However, for the sake of convenience, we can expand the 3x3 matrix into a 4x4 matrix, which allows to directly incorporate the translation from the offsets x origin. The combination of these four transformations then forms the so-called affine transformation. In the subsequent programming lecture and corresponding UPython notebook, you will learn more about how to transform between voxel and physical coordinate space and why the trick of expanding the 3x3 matrix into the 4x4 matrix actually works. Now that you have powered through the last rather theoretical notebook, it is really time to get into practice. After the next and final notebook of this section, we are ready to tackle medical problems with deep learning. Thank you